Chapter 4. A computer in someone else's building. The Nimbus app was running on Tom's laptop. That was fine for showing investors a demo. It was not fine when Maya pressed launch and 200 restaurants signed up in the first week. Tom's laptop was now handling real orders, real menus, and real customers. Sitting under Tom's desk, running off the office Wi-Fi, plugged into a power strip that also powered a space heater and a coffee maker. "We need a server," Maya said. "A real one, running somewhere that isn't under your desk." Tom looked at his laptop. The fan was audible from across the room. That was when they started looking at what it actually means to rent a computer. The abstraction nobody explains. When people say their application runs on the cloud, they usually mean it runs on a virtual machine, a computer that doesn't physically exist as dedicated hardware, but that behaves in every way like it does. Here's the mechanism. A physical server in an AWS data center has a lot of resources: CPU cores, memory, disk, and network bandwidth. AWS takes that physical server and divides it using software called a hypervisor. The hypervisor creates multiple virtual machines, each appearing to have its own dedicated CPU, memory, and disk, but actually sharing the underlying physical hardware. Each of those virtual machines is what AWS calls an EC2 instance. EC2 stands for Elastic Compute Cloud. The elastic part is important, and we'll get to it. For now, an EC2 instance is a computer you rent by the hour. It has an operating system, a network connection, and computing power. It runs your application just like a physical server would. The analogy: renting an apartment in a large building versus buying a house. The building owner, AWS, maintains the physical structure: the plumbing, the electrical, the security. You get a unit. You furnish it however you want. You pay monthly or hourly. When you need more space, you move to a larger unit. When you move out, you stop paying. Choosing your instance. Size matters. Not all EC2 instances are the same. AWS offers hundreds of instance types, organized into families based on what they're optimized for. General purpose, e.g. T3, M6i. Balanced CPU and memory. Good default choice for most web applications. Compute optimized, e.g. C7G. More CPU relative to memory. Good for video encoding, scientific modeling, batch processing. Memory optimized, e.g. R7i. More memory relative to CPU. Good for databases, caching, in-memory analytics. Storage optimized, e.g. i3, high-speed local storage. Good for data-intensive workloads that need very fast disk I/O. Accelerated computing, e.g. P4. GPUs attached, good for machine learning training and graphics rendering. Each family has sizes. A T3 Micro has 2 virtual CPUs and 1 GB of memory. A T3X Large has 4 virtual CPUs and 16 GB. You pick the right size for the workload. Leo had chosen a T3 Micro. "How many users can a T3 Micro handle?" Tom asked. "Depends on the application," Leo said, "but probably not 100 concurrent users running image uploads and database queries." Tom wrote T3 Micro on the whiteboard and drew a sad face next to it. The AMI, your machine's starting state. Before you launch an EC2 instance, you choose its operating system and initial configuration. In AWS, this is called an Amazon Machine Image, AMI. An AMI is a template. The operating system: Amazon Linux, Ubuntu, Windows Server, etc. Pre-installed software. The initial disk state. When you launch an instance from an AMI, AWS creates a fresh copy of that template just for you. You can also create your own AMIs. If you configure a server exactly the way you want it, you can save that state as a custom AMI and use it to launch identical servers quickly. This is how you deploy consistent environments at scale. Think of an AMI as a recipe. The recipe describes the meal. Each time you follow the recipe, you get the same meal. If you want to change the meal permanently, you update the recipe. Key pairs, the right way to access a server. Remember the admin 123 disaster from last chapter? The correct way to log into an EC2 instance is with a key pair. A key pair is a cryptographic pair, a public key stored by AWS on the server, and a private key, a file you download and keep secret. To log in, you use SSH, a secure protocol, with your private key. There's no password. If you lose the private key, you lose access. There's no forgot my password for SSH. This matters because key pairs are unique to you, cryptographically impossible to guess, not stored by AWS, you keep the private key. Easy to revoke. Delete the key from the server, generate a new pair. Priya had already set up key-based access on the Nimbus server. The admin123 server was decommissioned. Nobody was sad about it. Instance lifecycle, not forever. This is something many beginners miss. EC2 instances are not permanent by default. When you stop an instance, the compute resource is released. When you start it again, it might run on different physical hardware. Any data stored on the instance itself, on its root volume, survives a stop-start cycle, but the public IP address changes. When you terminate an instance, it's gone. Unless you have separate storage attached, which we cover in Chapter 6, any data on the instance disappears. This ephemerality is actually a feature, not a bug. It means you can spin up servers, use them, and throw them away. It enables horizontal scaling. But it also means you should never store important data on the EC2 instance itself. Where does data live then? In separate storage. We get to that in the next 2 chapters. What elastic means. We said EC2 stands for Elastic Compute Cloud. What's elastic about it? 2 things. Vertical elasticity. You can change the size of an instance. Stop the instance, change it from T3 micro to T3x large, restart it. More CPU and memory, same application, same setup. Horizontal elasticity. You can add more instances. Instead of 1 large server, run 10 medium servers behind a load balancer. When traffic drops, remove instances and stop paying for them. Both approaches solve the one server too much traffic problem, which we explore in Chapter 7 when we add auto-scaling to the story. The key insight. With EC2, computing power is something you dial, rather than something you buy. Need more? Turn up the dial. Need less? Turn it down. Pay accordingly. Strengths and limitations. Why EC2 is powerful. Full control. You choose the OS, the software, the configuration. It's your computer. Flexible sizing. Hundreds of instance types across every use case. No hardware to manage. AWS handles the physical layer. Pay per second billing. For most instance types. You stop the instance, you stop paying. Works with everything. EC2 is the foundation that most other AWS services are built on. Where it gets complicated. You're responsible for patching and updating the operating system. Shared responsibility model. This is the in-the-cloud part that's yours. Managing EC2 at scale means managing instance state, AMIs, security patches, and lifecycle across potentially thousands of machines. That's operational overhead. EC2 is not the right answer for everything. For event-driven code that runs infrequently, Lambda Chapter 20 is cheaper and simpler. For containerized workloads, ECS and EKS, Chapter 21, offer better resource efficiency. Unused instances still cost money. If you stop an instance, you stop paying for compute. But if you have storage attached, you still pay for that. Summary. An EC2 instance is a virtual machine you rent in AWS. It has an OS, network access, and compute resources. Instance types are organized by use case. General purpose, compute optimized, memory optimized, storage optimized, accelerated computing. Pick the right family and size for your workload. An AMI, Amazon Machine Image, is the template for your instance's OS and initial configuration. Custom AMIs enable consistent, repeatable deployments. Key pairs are the secure way to access EC2 instances. No passwords. EC2 instances are not permanent by default. Terminated instances lose their data. Store important data in separate storage services. Elastic means you can scale compute up and down, both vertically, bigger instances, and horizontally, more instances. Exam tips, SAA CO3, Domain 3, Task 3.2, High-Performing Compute Solutions. Shared responsibility for EC2. You are responsible for patching the OS. AWS maintains the physical hardware and hypervisor. This is a frequently tested distinction. Instance families matter for scenario questions. If a scenario mentions high memory requirements, in-memory cache, SAP HANA, the answer likely involves a memory-optimized instance. If it mentions batch processing or HPC, compute optimized. Stopping equals terminating. Stopping an instance preserves it. You can restart. Terminating deletes it. Exam scenarios test whether you know this distinction. Public IP changes on restart. If your application needs a stable IP address, use an elastic IP, a static public IP that stays associated with your account. This costs money if you allocate one and don't use it. On-demand, reserved, and spot pricing models are tested heavily in Domain 4. We cover them in Chapter 27. For now, know that on-demand means pay by the second with no commitment. Exercises. Exercise 1. Recall in your own words. What is an EC2 instance? What is an AMI? What is the relationship between them? Hint, think about the recipe analogy. What's the recipe and what's the meal? Exercise 2. Exam practice scenario. A company is deploying a high-traffic web application. The application handles product catalog searches with complex filtering logic that is CPU intensive. The team expects significant traffic spikes during sale events. They want to ensure they choose the right EC2 instance type and are prepared for traffic surges. Which combination of choices best meets their requirements? A. Memory-optimized instances with a fixed number to ensure consistent performance. B. Compute-optimized instances with auto-scaling to handle traffic spikes. C. General-purpose instances with a single large instance size. D. Storage-optimized instances because the product catalog requires fast disk access. Hint 1. The workload is described as CPU-intensive. Which instance family is optimized for CPU? Hint 2. The scenario mentions traffic spikes during sale events. A fixed number of instances won't efficiently handle variable traffic. What AWS feature handles this? Hint 3. Compute-optimized instances handle CPU-heavy work. Auto-scaling adds and removes instances based on demand. Together, they answer both requirements. Answer B. Explanation. Compute-optimized instances like the C family provide more CPU per dollar for CPU-intensive workloads. Auto-scaling automatically adjusts the number of instances based on load, adding instances during sale events, removing them when traffic returns to normal. This combination optimizes both performance and cost. Why not A? Memory-optimized instances are designed for workloads that need large amounts of RAM, databases, in-memory caches. This is a CPU-bound workload. And fixed instance counts means either over-provisioning, waste, or under-provisioning, failure. Why not C? General-purpose instances trade some CPU efficiency for balance. For a known CPU-intensive workload, compute-optimized is more appropriate, and a single large instance is a single point of failure. Why not D? The bottleneck is CPU, not disk I/O. Storage-optimized instances are designed for workloads that need very high throughput to local storage. SAA CO3 Domain 3, Task 3.2 Exercise 3, Architecture Challenge, Optional. Nimbus currently runs a single T3 micro EC2 instance for the entire application. The team needs to decide, upgrade to a larger instance T3.2x large, or add more T3 micro instances behind a load balancer. Walk through the trade-offs. What are the advantages of each approach? What questions would you ask to decide? Hint, think about single points of failure, cost, deployment complexity, and what happens during maintenance. There is no single correct answer. This is about reasoning through vertical versus horizontal scaling. Post-credit scene. Leo spent the afternoon resizing the server. He moved from a T3 micro to a T3 large. The CPU dropped to 30%. Pages loaded in under a second. Tom watched the AWS bill update in real time. The new instance cost 4 times more per hour. He made a note. Maya was looking at something else on her screen. Leo, she said, while you were resizing the instance, the website was down for 12 minutes. Leo looked up. We had a queue of 200 unfulfilled orders. He looked at the screen, then at the ceiling, then back at the screen. We need something for our images, he said, changing the subject slightly. Right now, uploaded menu photos are saved directly on the server. If we resize or restart the instance, do we lose them? Priya already knew the answer. In the next chapter, where files live when there is no hard drive to point to.